Hi, this is going to be a 2P04 test redo to give you some practice with actually solving practice problems. So we're going to do the 2017 test number 1 from 2P04. Okay, so here's the first question. It has 4 different parts there. Block lifting. A block of mass 15 kilograms, right there, is on a ramp subject to kinetic friction with that coefficient. Block is also being pulled up the ramp by a rope attached to a pulley with an electric motor. Because the electric motor has a control system that literally can't even right now, it applies a torque to the initially stationary block given by this equation. So we've got some negative t squared over 2 seconds there, some sine squared of t over 1 second plus 1, some pretty complicated things. Definitely going to want numerics in order to deal with this. In a clockwise, that is raising the block direction to the pulley, and the pulley itself is a solid cylinder of mass 5 kilograms and radius 0.5 meters. Now we're told to assume that there's no other friction on the pulley, so its only torques are from the control system and the tension in the rope attached to the block. And also, the block's velocity is always up the ramp when riding friction. That's going to make things easier so that the friction is always going to be in the down the ramp direction if the block is always moving up. And that the rope is light and doesn't stretch. So that means we don't have to consider its mass. We don't have to look at any spring effects in that. Okay, first thing, draw a free body diagram for the block and the pulley. So let's make a free body diagram. You could take a picture of this with your phone, but let's imagine it's a test scenario. So what I'm going to do is open up paint.net here and maybe zoom in on this thing. So we've got our block. It's not a very good picture of that. Maybe we'll take a screenshot of this thing. You could use the snipping tool or any other screenshot device. That's a little bit better. Okay, now within paint.net, it's you can use any other program to do this that's convenient for you. I like this one. So it's got some keyboard accelerators, some shortcut keys for things like a line. You can put an arrowhead at the end of it like that, and then draw different things on the diagram. Let's use a different color so that we can see things a little bit more easily. So where is the color selection again? Color palette. Color palette. Okay, there we go. It was off. It was turned off. Button up there at the top is going to fix that. Okay, what's a good color for some arrows here? Let's take some maybe magenta, sort of a magenta day. All right, now we have a normal force. Hitting T will allow us to label that normal force there. And now let's go back over to the line. We'll pick a different color for a different force, may as well. Right from the center of the block, we've got a force down, which we're gonna label W for weight. And we're gonna need a friction force. Friction force is always gonna be down along the ramp, applied at the bottom of the block there. And that would be force of friction. Then we can label the tension in the rope. So how about some blue for that? Force going along the rope direction there, and that would be the tension. So that's the free body diagram. Really, to get this as a free body diagram for just the block, we want to be drawing the block by itself. So what we'll do is select just that part of it. And now it's like the ramp is just specifying the angle there. So here's a free body diagram for the block. That should be all the forces on that. And for the pulley, we can go and redo some of the same stuff. So we'll have a tension force going down. Just need to expand the area that we're allowed to draw in there. Maybe something like that. Tension force going down. And also we're going to have a torque around the center there. So let's maybe draw the, oh, you know what we'll do? We'll get rid of the arrowhead, and then we'll sort of create a circle by something like that, and then put the arrowhead back on. There. Now we've drawn a perfect kind of arc that gets the point across there, and we'll label this tau. Tau, yeah. Okay, cool. So selecting that, Control C, and then paste that over here. Now we've got our free body diagram for both the block and the pulley. All right. Okay, so now we're going to write the Newton's second law force balance equations for the block and the pulley. The net force on the block is equal to its mass, little m, times its acceleration. And this is going to be in the x direction, T minus the friction force minus W sine of Q. Let's just call that angle Q. And in the vertical direction, that's going to be N minus W cos of Q for that angle theta. Now this is equal to the mass times in the x direction, that's going to be acceleration, and in the y direction, that's going to be 0. So that's the force balance equation. Then we also are going to have a torque balance equation. So the net torque on the pulley is going to be equal to its moment of inertia times its angular acceleration. And the net torque on the pulley is negative r times the tension plus the tau at t from the control system, and that's going to be I alpha again. Okay, so there we go. There's our force balance equations for the block and the pulley. Next thing we're going to need to do is write an expression for the block's acceleration as a function of time. So in other words, solve these equations for the acceleration and put everything else into the variables given in the question without necessarily subbing them in for their values. So now we're going to jump over to Maple to give this a shot, and we're going to type in our equations. So I'm using Shift Enter to go to the next line here. Shift Enter. The first equation is the X force balance equation, T minus FF minus W times sine of Q is equal to M times A, and N minus W times cos of Q is equal to 0. Then the angular acceleration is negative r times t plus tau is equal to, we can't use I because that's Maple's symbol for the square root of -1. Yeah, so you can see that I is a predefined thing in Maple. So we need a different symbol. I would usually use MOI to be a moment of inertia times alpha. So that's one set of equations, but in fact we have a number of additional equations that are necessary to turn some of these quantities into the things that we started with. So we need to tell Maple what the friction force is, that's just the mu k times the normal force. We need to specify that the moment of inertia of a pulley, if it's a solid cylinder, is half big M, that was the mass of the pulley, times r squared. We need to relate the angular acceleration to the linear acceleration. So alpha r is equal to a. That's because the rope doesn't stretch. And we need to tell it what the weight is. We need to say that W is equal to M times G. So this is the total set of equations. Oh, we need a comma here. Okay. So there. Now that we've got this set of equations, we can determine what the acceleration is. So we can try to solve this set of equations for the variables that we want. Now, if you just say solve, there's a lot of unknowns in this equation that Maple doesn't know that we need to solve for. So it says like Q is Q, M is M, R is R, big M, G, alpha. It's assumed that alpha is a thing that we want the rest of the expressions in, as long as and that part is not correct. We actually wanted to eliminate alpha. So in order to get this out of the expressions, we want to do that because that's not one of the things we started with. We need to say specifically what we want to solve the equations for. So we want A, and we want to eliminate everything that wasn't given in the problem. So what other things do we have in these equations that weren't variables that we know as constants in the question? So we'll eliminate alpha, we'll eliminate the tension, we want to eliminate the weight, what else? MOI, moment of inertia, the friction force, and the normal force. And we should have 7 different things here that we can eliminate because we have 7 equations. So there we go. Now we've got expressions for all the different pieces there. If we want to just extract out what the acceleration is, then we can specify that as acceleration equation is equal to opening, because this is a list of lists, we need to open it. So you see now it's not a list of lists. See, there's only one square bracket at the end there. And it's the first equation in that. It's always going to be the first one because that's the order that we gave the A in. So we can rely on that, suppress this output, and then say extract the first item from that previous list. And there we go. We've got our acceleration equation there. If you want, you can suppress this output too. And there we go. Acceleration equation. Write an expression for the block's acceleration as a function of time. And everything else is in the variables given in the question. So we are good. Mission accomplished. Next part is going to be to solve for the velocity as a function of time and plot it for t is 0 to 5. To do this, we're going to need to substitute in the constants. So what I'm going to do is make a new list which has all the variables in it. So what do we need? We need R in this problem is 0.5. Little m is 15. G is 9.81. We'll need to tell it that. Q, the angle, is 35 times pi over 180. So Maple is case sensitive. Capital P, small I, is 3.14159. Let's just point this out. These are all different symbols. The only capital P, small I is a predefined thing. The other ones are just referring to the Greek letters that you can assign to different variables in a problem than actually 3.14159, etc. So watch out for that. So that's our angle. We needed to multiply by pi over 180 to convert it to radians, so that when we take the sine and cos of it, we're going to get the right answer. Maple is expecting radians. What else don't we have? The pulley mass, which is 5, and the torque expression. I have to be careful to type this in correctly. Tau is equal to 80 times e to the negative t squared over 2, plus sine of t plus 1. We don't have to worry about the divided by 1 second. That's just to say that the time itself has to be in units of seconds, and same with the seconds up here. T plus 1, all squared, and that should be good. Let's just have a look and see that everything makes sense in this. Did we forget any variables? I don't think so. Oh, mu k. Yeah, so mu k is equal to 0.3. Okay, now that the variables are established there, we can solve the acceleration equation in a couple of different ways. So first, let's just say integrate. So velocity will be the integral of substituting the varies into the acceleration equation. Really the right-hand side of this. So integrate that with respect to t. There's our velocity. It has some error functions in it. That the error function is something that just expresses the integral of e to the t negative or positive t squared. So it's a defined thing numerically, but it's we can't really write out a closed form expression of it without making a new function. It's not expressible in terms of functions that you know already besides the error function. So we can plot that. Plot v from t is 0 to 5. All right, now one concern with this you'll notice is that the velocity doesn't start at 0. And that's because this method of solving for the velocity doesn't guarantee that we're going to get actually the integral that's shifted vertically to the one we want. We just took an integral of this acceleration expression, but we didn't necessarily get the right one. So a couple of ways you could do it. You could do this, and then you could evaluate what the velocity at 0 is and correct it, but by maybe. So what I mean by that is valf subs t is 0 into the velocity, and it's 2.493 that we got from this. So what you could do is just declare that it's the thing minus 2.493, and now it starts at 0. But that's kind of messy. So a better way to do it would be to just use dsolve, which lets you specify initial conditions. So what we're going to do is take, in addition to substituting in these variables, we're going to substitute in that a is equal to diff of v at t with respect to t. Then subs vars into the acceleration equation gives us this expression. So now we've got an actual differential equation for v, which we can solve with dsolve. These plots and valfs are not working right now. Dsolve the previous thing along with the initial condition that v at 0 has to be equal to 0. Okay, now we've got some expression for velocity where if we were to assign that, then evaluate substituting t is 0 into v at t, we end up with 0, and we can plot it and get the correct expression that starts at 0. Okay, so there we go. We have gone and solved for the velocity as a function of time. Well, I guess, let's also fix up the legend on this plot. So we can do that with, I believe, the, let's see, labels command? It's either labels or axis. We'll just try one. Time in seconds. Velocity in meters per second. Let's try that. Yeah, there we go. Labels. So labels will allow you to label the plot axes, and that's a nice clean solution for that. Okay. Another thing that we can do is solve this same problem in FlexPDE. Let's give that a shot. So here's a new file in FlexPDE. We can make the title something like 2017 T01 video magic, and then set up the rest of the problem. So we're going to be having we're going to convert this to a time dependent thing, which means we need to set a threshold for the variables. Let's use v as the variable. What else are we going to need? We'll say the equation is dt of v is equal to acceleration. This is a new way to do things. So under the definition section, we can just write out what the acceleration expression is. Let's imagine that we haven't used Maple for very much except for going and solving this equation, which we could have taken from our the equations that we started with and just isolated manually without using Maple. Maple's still kind of convenient to use to do that. So we will imagine we know this part, and we're going to go and type that in Flex. Okay, so the acceleration is -2 times r times mu k times m times g times cos of q plus r times m times g times sine of q minus tau. And we're going to divide that by r times 2 times m plus big M. Now the problem is that FlexPDE, unlike Maple, is case insensitive. So this big M is going to be the same variable as little m, which means we need to give it a different symbol, a different label, M pulley, maybe to distinguish from the pulley mass and the mass of the block. So there's the acceleration that we've gone and written in. We also need to define what all of these different constants are. And the syntax in Flex for this is almost the same actually as the syntax in Maple. So let's just go and copy most of this variables code here and paste that into the definition section 2, eliminating the commas changing this to M pulley, and yeah, okay. So then what we're going to need to do is say the time range. We wanted to go from 0 to 5 seconds, and we're going to need to change this to a history plot. History of V at 0, 0, and say what time range we wanted to plot for. So this, remember, is the solving time range, and it's not necessarily the plotting time range. So for t equals 0 by 0.12 n time will let us plot the velocity with this history plot. Okay, did it work? Yes. Now you'll notice that we got the same expression as we found in Maple there. One thing is we didn't even specify the initial values. That's because the default initial value is v equals 0 for the variables that you're solving for, so you don't actually need to tell it that. Again, we're not considering any spatial dependence, so we can eliminate the really dense grid with n grid equals 1 to make it a little bit faster. You can see that's kind of noticeably faster to get that solution. If you wanted to get what the velocity was at the end, then you could use the summary syntax. So maybe we'll put this in caps to make it easier to see. But again, Flex is not case sensitive. So now let's see, what is eval v 0, 0, 0? No, that's not it. It's not eval. What is the syntax for that? Ah, report eval. Okay, so pretty small font here, but it actually is saying what the quantity is. You can give a label to that. As final velocity. And there we go. Now it's labeling out final velocity in the summary box. Is that the same as we got with Maple? Let's check. Subs t equals 5 into v at t. And evaluate that. Yeah, 3.174. Okay. Okay, so part number 2. For the same block, find now the position as a function of time and plot it for t is 0 to 5 seconds. Let's have a look at adjusting Maple to do this instead. Well, what we can do is, instead of substituting that a is the derivative of velocity, let's say that a is the second derivative of position. And then we're going to be solving the equation under the condition that x at 0 is 0 and d of x at 0 is 0. So starting from rest at position 0. Now the thing that we're getting is going to be the position as a function of time. We can plot that and label it position and figure out what the final position is, like so. So there's the position as a function of time, and there's the expression for it. So not that bad to do kind of the same sort of thing, switching it to a second derivative in Maple. What about in Flex? So in Flex, to calculate the position as well, we're going to need another variable there. What do we want to use for position? How about u? Because x is already taken. So u, and then we're going to need to say that this is the differential equation for v. The differential equation for u will be that u is the derivative, that the derivative of u with respect to time is the velocity. So the rest of the program should work just the same now, but we can also make a history plot for the position. Okay, and that looks the same as the one that we calculated in Maple. Then they wanted us to determine when the position of the block is 20 meters from the starting point. Let's see how we would do this in both programs. Here the strategy diverges a little bit. So in Maple, once we have found an expression for the position, we can do it a couple of different ways. You can zoom in on this plot around where you think it should be 20. So let's suppress a lot of this output that was taking up the screen real estate there. And we're also going to suppress the acceleration equation. That substitute, great. So you can zoom in. It looks like 20 is between about 2 and 3. So let's go from 2 to 3 here. And now it looks like it's around 2.8. So let's say 2.6 to 2.8. We've gotten pretty close, and you can continue like this, just zooming in on the plot until you get as arbitrarily close to 20 as we like. So the answer is going to be around something like 2.72. But a more elegant way to do it is to use fsolve. So fsolve x at t is equal to 20 for t in the range of, let's say, 2 to 3. And it says 2.707777. That seems like it's what we were thinking from the plot. So somewhere in there, that's the time where the position is 20 meters from the starting point, using fsolve there to search for where position is 20 and giving it a time range. In FlexPDE, the way to do this is with a halt condition. So in the run part here, you can also say things that will make the conditions where if they become true, you'd like the program to just stop. So let's halt on u is greater than 20. And this has stopped the run of the program as soon as u has become bigger than 20. The final u that we can report the final position as well, actually. Let's do that. Report u as final position to see how close we got. So 20.11 for this setup. We've gotten with the time stepping that we were taking, we ended up stopping at just slightly above the position where it's exactly equal to 20. So this is a little bit rougher, but we still have all of the values for this. So what time was it? 2.7334. If you want to be more precise, then you can go back into the plot part here and change the time range to have a smaller time step. So by going from by 0.01 instead of 0.1, then that tells FlexPDE that we want to take much finer time steps, and we'll catch different different things in the different events in the final position. So now we've got a final position that's much closer to 20 at a time of 2.71. You can try narrowing this down further and see if it's possible to approach the answer that that Maple gave you for this. The last part is find the position of the block when the velocity first becomes 0. So now we need to have the velocity as well as the position in Maple. So let's also define v is the derivative of x at t with respect to t. And we can go back to having a look at what that looked like. Plot v from t is 0 to 5. And the velocity is actually not 0 after the start at any point in this range. So we're going to need to increase the time range. Let's try 7. Yeah, so it looks like it becomes 0 somewhere between 5 and 6. And in order to zero in on exactly where that is, we could once again just zoom in the plot or use fsolve. So this time we'll say fsolve v equals 0, and because v starts at 0, we have to give it a time range. If we just say fsolve v equals 0, it's going to give us 0 because, well, when t is 0, that's the first time the velocity is 0. But we don't want that time. We want the time in this range. So we can specify a range that we want fsolve to search in. So t equals 5 to 6 will let us zero in on that one that we're interested in, and that's 5.473. That's how you can do it with Maple. For Flex, in order to figure out when this first has a velocity of 0, we're going to change our halt condition to v is less than 0, and we're going to go from to a larger value here. So let's say 6. And there we go. We've zoomed in on when it is that it stops. We found 5.48 in Flex compared to the 5.473 in Maple. We could make Flex more precise by narrowing down the time, although that's going to increase the amount of time it takes to run this simulation. So two very different approaches to the solution method in order to answer this same problem. Giving us the same kind of answer makes it a lot more likely that we haven't made a silly mistake somewhere. Okay, thanks for watching.